Hi, welcome to this video series on cryptography. Today I will talk about a problem related to symmetric encryption. The question I'm trying to answer is the following. Is it possible to construct symmetric encryption schemes using the discrete log hardness assumption? Okay, I will explain briefly what a discrete log hardness assumption is later. But the core idea turned out to be very interesting, and it was developed back in 1970s, mid of 1970s. The algorithm name is actually Pohlig-Hellman Cipher algorithm, and it is having a remarkable similar structure comparing to Diffie-Hellman key exchange. So let's get straight into the algorithm. Okay, so what is the algorithm? We are talking about symmetric encryption, right? So we would need encryption and decryption function. Of course, we need a symmetric key to encrypt and decrypt. So this is the basic foundation for any symmetric encryption scheme. So let me start now with the encryption function first. So encryption function, of course, we need a message that you want to encrypt, right? It takes the message and writes it to the exponent e, okay? So, and then mod p, okay? So this is encryption function. And decryption function is also the same structure. Let's say, let me call this answer, right, as C. And if you have an encryption of a message M, you will get a ciphertext C. And you would be decrypting your ciphertext as C using a decryption function. Okay, so what is this E and D? We need to define what E and D, okay? E and D, you can call E as encryption a key, right? This is the key used for encryption, and D is the decryption key, okay? So these are all foundations of pretty much any symmetric encryption scheme. In regular symmetric encryption scheme, your E and D are equal. Here it's not, okay? That's the only difference. Okay, so another important thing is that how is E and D connected to each other? Otherwise, we wouldn't be able to decrypt and get back the message M, right? So how do we do that? It turned out that we can derive E and D in this fashion. Okay, as long as E and D are having this interesting property, we are good to go. Okay, why is this needed? If this is true, okay, what can we do? Well, okay, well, if this is true, we do know for sure E dot D can be written as some constant time minus 1 plus 1, right? This is the definition of mod function anyways. So what can we do now when we do decryption? Let's consider the decryption now. We do C power D, right? That's the purpose of decryption. How did we produce C at the first place? We produced C at the first place by doing M power E. So which means we have M power ED, right? Okay, which we can rewrite it like this is K times P minus 1 plus 1, right? That's basically the meaning of E dot D or E times D. And now we can rewrite this a little bit using the properties of exponent, right? Into M, okay? And this is nothing but what is M power K times P minus 1? M power P minus 1, and for that we can apply exponent K, okay? That's basically what we are doing. Okay, what is M power P minus 1? Okay, so now comes our Fermat, okay? Fermat's little theorem. Okay. Fermat's little theorem tells us that A power P minus 1 is congruent to 1 mod P, okay? So this is basically the Fermat's theorem. And we are now applying Fermat's theorem to the above equation. So we should be getting, this will become 1, right? Okay. So 1 power K is 1, so who cares? So it's M. So that's the reason why decryption gives us the original message M, okay? So this is basically it. We need an encryption key and a decryption key. Of course, we need a prime P, otherwise this Fermat's theorem won't work. Fermat's theorem assumption is P is a prime. Okay, so this is basically the algorithm of Pohlig Pohlig-Hellman exponential cipher. Okay, I will compare this with RSA very briefly and very quickly. In RSA, it has more or less a similar structure. Instead of P as a prime here, in RSA, we would have a composite number, which is made of 2 or more primes. Okay, and the encryption key E is made public in RSA, but in Pohlig-Hellman, encryption key and decryption keys are private. And in RSA, your E.D is actually having a similar structure like this, except that it's not pi minus 1, it's phi of the Euler-Torsion functions used. Okay, this is the only difference, okay, between RSA and Pohlig-Hellman cipher. Okay, so having said that, now let's do a quick implementation and then study this algorithm by using a concrete implementation. Okay, so I will now get back to my implementation. I did a quick implementation using Python, and I'm going to now use an online Python compiler to compile and run this thing for us. Okay, so what is the first thing we need? Of course, we need to generate encryption and decryption keys, right? So here's the key generation part. I'll just hide this to create some space for us. Okay, so we need an exponent E, which is the encryption exponent, right? A random number. I'm using ZP star, right? In my demo, the group is ZP star. So I pick a random number below P that becomes my exponent E. And then remember, I need another exponent D. So I also shown you that E and D must have an interesting relationship. They must be 1 mod P minus 1, otherwise you would not be able to decrypt. And for that to work, remember, P is a prime, therefore P minus 1 must be an even number. And you can't solve this equation E times D equal to 1 mod P minus 1 unless your E is odd, right? If E is even, P minus 1 is also even, therefore you will not be able to find a multiplicative inverse. Okay, so E has to be odd. That's the prerequisite. And in other words, E must be relatively prime to P minus 1. Otherwise, this equation won't be solvable. Okay, this equation wouldn't have a solution for D. So this is coming straight from the basic congruence relationship. Okay, so this is what the key generation algorithm does. It picks a random E and then it tries to figure out whether it is relatively prime to P minus 1. If it is, then it knows how to find the decryption exponent D. That's basically the part that you're seeing here, and that's all. So once you have this, you have generated the keys. Otherwise, you will throw the old key E and keep trying until it finds a good E and D, which is very quick. Okay, because that's the reason. One of the reasons why we are working in a prime group, right? It's a Z star P, okay, or ZP star. Okay, so this is not many iterations. This is going to terminate very quickly. Most of the odd numbers will satisfy this property. Okay. Okay, so many odd numbers will satisfy this property. I'm not going to formalize exactly how many times this loop will run to do the key generation. That's pretty quick, as you will see in my demo. So what I'm going to do now next is to show you the encryption function and the decryption functions. Encryption function is very simple, right? M power E mod P. So similarly, decryption function is C power D mod P. As you can see, encryption and decryption, there's no difference. I could have written just only one function, but just for readability purpose, I wrote 2 different functions. Okay, so we have encryption, decryption, and then we have our test code here. Okay, so I wanted to show you how I will be able to encrypt this message. Demo of Pohlig-Hellman cipher, right? So I convert this string into an ASCII using this little Python magic that will give me a number. The number is basically ASCII encoding of the string. That's not encryption, by the way, just converting it to a number, because in cryptography we deal with numbers, not with strings usually. So and then I need a prime P, as you have seen. So I took a prime from my RFC 7919, and then I call my key generation function. It will generate me an encryption and decryption keys, right? What am I asserting here? I'm asserting that when I decrypt the ciphertext C, I better get the message M. Okay, that's basically what I assert. And then, okay, let me run this first, and then I will go into another important property called commutative cipher. Okay, so now I'm running it, and here you go. What you're seeing here is basically just the printout of this message M in ASCII, right? In ASCII, what is D? D is in hex 45, right? A is 41, 42, 43, 44. Okay, it's 44. Okay, so it's 44 in hex, which is 64 plus 468. So 68 is what you're saying here. Okay, that so you can compute the rest. Okay, so this is basically the ASCII representation of the message, and here I am actually doing the encryption of the message, and I get the ciphertext, and then here I am decrypting it. Okay, so we can actually even print the ciphertext C, and also print the message. It should be the same message as the message that we send in, otherwise the assert would have failed. So we can now quickly run this thing, right? Right, let's run it. Okay, so we can see here that where can we see? Okay, we are here. Here we can see. Here is the message that I mentioned we are encrypting, and here is the same. This is the ciphertext. So you can see that we get back the original message. This was the original message, right? We encrypted it. We got this big bulb of data, and then we got the except the last line also. Okay, this is the original message after we decrypt. Okay, so this is basically how the Pohlig-Hellman algorithm works. It's essentially same as the Diffie-Hellman key exchange from a high-level structure perspective, and it has a very remarkable structure comparing to RSA, which is more or less the same, except that instead of prime, it is using a composite number. Other than that, it's remarkably similar. Okay, so I actually don't know who invented first. Is it Pohlig-Hellman or RSA? But anyway, that's not important for our discussion. Now I want to show you some important properties. Okay, so why is this first of all secure? What is the security structure or our reasoning here? As you can see, our encryption algorithm is actually based on the fact that we compute the ciphertext, right, C, by taking M rising into power E mod P. So it's similar to Diffie-Hellman key exchange, but in the Diffie-Hellman key exchange, instead of M, we have a group generator G, which is public. Here, M is private, E is private, and it's difficult to find in general the value of E given C and P. Okay, even if somebody figured out what is M, it's still difficult to find E. Okay, so that's basically the hardness assumption that I was referring to in my problem statement. Okay, so having said that, now let's move on to the commutative property of this cipher. Okay, this cipher has an interesting commutative property, which I'm going to touch upon in a couple of more video series as I move into somewhat of a foundation of homomorphic encryption schemes. Okay, so what is commutative encryption or commutative cipher? So the idea of commutative cipher is that if you have two different keys, say E and E2, it doesn't matter in which order the message was encrypted, you get the same ciphertext. Okay, so let me first write it in symbols here. So what it means is that if you have a message M, so what you're doing is you're doing encryption of your message M, right, using say the key E. Let me leave the P. P is the prime that's fixed anyway. So we do this, right? And then we again re-encrypt it, okay, using say another key. Okay, so what's happening here? We basically double encrypted the message M, right, using two different keys. Okay, we are saying that this is equal to encryption of take the message M, encrypt using E2, and encrypt that using E. We are saying these two are equal. That's basically commutative property, right? It doesn't matter what order the keys are applied, you get the same ciphertext. This is not true for our AES, for example. If you encrypt a message using AES and re-encrypt it with another key, you will get a different ciphertext comparing to the different order. Okay, so if you change the order of the keys, you will get a different ciphertext. But that's not true here in Pohlig-Hellman algorithm. That's basically due to the fact that how we define encryption. We define encryption by taking m power e mod p, right? So if you apply now, say, encryption of m comma e, right, and again encrypt it using another key, say e2, or say e2 is not so nice. Okay, so anyway, let's call it e2. Okay, so 1 2 is equal to what is, how did we get the m comma e encryption? We got this by m power e, and then we have our e2, right? Okay, so we will now again encrypt it. So we get here m power e times e2. That's basically what we are having. Okay, because this is same as m power e2 power e, we could say this is nothing but encryption of m comma e2 and then e, right? That's basically it. So this is basically the commutative property. Okay, so we have demonstrated that Pohlig-Hellman algorithm is commutative. We also demonstrated that encryption and decryption keys are actually canceling out in an interesting way because of Fermat's little theorem. And one more important point that I would like to clarify is that this particular scheme is actually a deterministic scheme. Okay, what I mean by deterministic is that if you run it again, you should get the same output. See here, I get, for example, this big blob of ciphertext. Let's just remember the last 7 characters, right? 48466763, 48466763. Let's run it. Oh, I am sorry, why it's changing now? The reason it's changing because I'm regenerating the keys, right? If I fix the key, it wouldn't have changed. Here I'm regenerating every time. Okay, so that's you wouldn't do that when you are applying a symmetric encryption, not to regenerate the same key. So other than that, it is unique every time you run. Okay, well, let me clarify this to avoid confusion. If the keys are fixed, the key E and D's are fixed, the ciphertext won't change. Here it's changing because I'm regenerating this key pair again and again. Okay, all right, so that's basically it. So it's deterministic scheme. It is one more problem or limitation, if you want to call that way, although it's needed. Yes, it's malleable. Okay, what it means to be malleable is that, let's say I multiply my ciphertext by number 2, it will successfully decrypt. It won't even comply. Here it's complying because I'm asserting, right? So let me remove the assert for a moment. Okay, if I remove the assert, I think the comment is wrong. Let me fix that first. So if I now assert, I remove the assert now. So here you are seeing no error whatsoever, right? You get back some message m. Oh, I didn't even decrypt. Let me decrypt it here. Yeah, you see, the decryptor got some other message. At the time of decryption, there was no error message whatsoever. That's because this algorithm inherently doesn't have the notion of non-malleability. Okay, so it does have notion of malleability. Okay, so that is needed for homomorphic encryptions usually. Okay, so so let me wrap it up by summarizing the key points that we learned today. So we learned that it is possible to construct cipher schemes or ciphers based on the fact that you have a discrete logarithm hardness assumption. And it is also interesting to note that this particular scheme is a commutative cipher. Okay, so it doesn't matter what order you apply your encryption keys, you get the same ciphertext. Okay, if the message is fixed, if you have 2 different keys, you can change the order, you get the same ciphertext. Why I'm stressing that? That interesting property is going to help us when we are going to look at say private intersection of 2 sets. Okay, I'm going to talk about that in the next segment. So this is going to help us. Okay, so although I have worked in this group Z star P or ZP star, you can actually apply the same algorithm in elliptic curve, right? There's nothing that stops you, because in elliptic curve you have exponents. You can, in exponents there means jumping around the points in a structured way, and you can do encryption decryption on an elliptic curve. So there's nothing specific to the group that I have picked up. Okay, so you need to pick a different curve instead of this particular group, and then you will be able to do the same. Okay, All right, those are the important properties that I would like to highlight today. And thank you very much for your attention.